So this is the middle third of the video is going to be constructing harmony and sound and all of our theory, or like all of what we've been trying to understand, constructing it all from scratch, just from physics, you know. Before there was music, there was physics and like a bit of maths. So it's going to be more technical, but you know, no worries about not understanding it fully, because it's going to get less and less technical the more we establish the basic concepts and then like get on with the more interesting stuff, I suppose. So basically, yeah, let's get started with that. So we start with sound. And sound is a wave, right? And so a wave is basically like energy that oscillates. So it kind of moves, you know, up and down, and it moves through space. And every wave has a fixed speed, and that speed depends on the medium it's in. It doesn't depend on anything else. So waves always move at the same speed. For example, air waves. So this is sound. Sound is a vibration in air. Always moves at the same speed, like 330 meters per second in air. And sound moves at different speeds through different materials, like say the string that we're going to be talking about here. But the point is, it always moves at the same speed in a given string, right? In a given sort of material, and that depends on like the string's tension and the density and all this shit. Doesn't matter. So a wave can be thought of as, you know, speed. The speed of a wave can be broken down into like the wave's wavelength and the wave's frequency. So the wavelength is like the wave kind of moves, and in moving it kind of pulses, right? And the length of that pulse, so for it to go up and then down and then back to neutral, that's the wavelength. And the frequency is the number of those pulses it does per second. So like the number of times the wave waves. And so if you multiply the frequency and the wavelength, then you've basically got like the wave distance times the number of times that distance is covered in a second, which tells you the total distance the wave travels in a second, which is the wave's speed, which we just said is fixed, right? So, okay. Let's think about then a string, right? Like this one. So basically, I'll bring up the little graphic that I have for this. This is the string, right? I have the full string that I'm demonstrating in shots from here to here, right? And when you have you can make a wave in a string by like plucking it, and then like the wave pulses out from here. But then when it hits the ends of the string, it bounces back. And so it can kind of cancel itself out if it bounces back. But there are some waves that don't cancel each other out, but they rather reinforce each other. And for that to happen, the wavelength needs to basically fit. So this diagram shows you what that wavelength looks like. So like the wave pulses, right? So the biggest possible wavelength is for the wave to go up and pulse and then bounce off here and then come down, because like necessarily the wave has to be at neutral when it hits the ends, basically. And so that forces it, in order to actually basically resonate with itself and build up something that we're going to be able to hear, it needs to have certain wavelengths that fit. And so like the biggest wavelength that fits is going to be, you know, double the length of the string, because it goes up and then it goes down. And every other wavelength that is possible, which is shown in this diagram, is a fraction of that. So it's either, so this is the fundamental wavelength, is this. But every other one that is possible it's either that, or it's half of that, or a third of that wavelength, or a quarter, or a fifth, or a sixth, up to infinity. And that means because the wave has a fixed speed, that means that the frequency is determined in terms of those wavelengths as well. So like where we have the fundamental wavelength, that gives us a fundamental frequency. But then half of that wavelength means double the frequency, because they have to multiply to the same thing, right? The fixed speed. And so the frequencies that are allowed are the fundamental frequency, and then 2 times that, 3 times that, 4 times that, 5 times that, up to infinity. And don't forget, frequency is pitch. It's the same thing when it comes to sound. So how fast the wave is vibrating is the highness of the note that we're hearing. So that means we are allowed only a certain number of frequencies on our string, and those are called the harmonics, right? We have the fundamental frequency, which you can probably guess is just this one, the fundamental pitch. And the reason for that is I pluck this, and obviously like the whole string vibrates most easily at that frequency. And we're saying like the other frequencies that we can hear from this string are the harmonics, like double, triple, quadruple, but we can actually go further than just kind of imagining ourselves hearing them. And if you put your finger over the top of the string, you don't press all the way down, but you just hover it there, then that basically forces the string to, not vibrate at that point. And so that's how we reconstruct the shapes that you see in the diagram. So these are, this is playing harmonics on the guitar. So I'll show you those, right? So this is the first harmonic is the fundamental. And then the second one is halfway along the string. And the third one is a third of the way. And a quarter, a fifth, a sixth, a seventh, and an eighth. It can be hard to actually find these. But yeah, I can just about hear the eighth one there. And you have the 9th, 10th, 11th up to, when you get into higher harmonics, you're getting into things that you can't hear as different notes anymore, but rather you're getting into things that you can hear as texture. The difference between a violin and a banjo, or whatever other instrument, like a recorder, clarinet, guitar, that's all determined by those, the higher harmonics that are not necessarily audible as different pitches. But yeah, those are the pitches, and that's what we can construct from our guitar. So I just showed off the first 8 harmonics, which are the same ones that are in this little diagram, right? So let's think about the 8 notes that we just constructed by doing this, right? So the fundamental, is that audible? Probably. This note. And then the second harmonic is this one, 3rd, 4th, 5th, 6th, 7th, 8th. So what do we hear in these notes? So these notes, the 1st, 2nd, 4th, 8th, 16th, 32nd harmonic, those are very similar sounding notes, right? And those are the octaves, that's me showing you the octaves. That's how the octaves are constructed. Those are literally double the frequency notes. And to us, these sound like they are basically the same notes. And so our first step in analyzing or understanding this harmony is to basically identify all of these, and instead of thinking of an infinite line of notes, we think of a circle of them, right? So we haven't yet constructed any other notes, but basically any node between, let's say this one, can be identified with the note double that, and so it does just go in a circle, right? But then we go further than that, and we say, well, our most basic ratio is doubling, so what's the next simplest one? Well, tripling the frequency, so the 3rd harmonic. So this relative to the second one, because we think these are the same note, is a ratio of 3 halves. And we've picked 3 halves rather than 3 just because it's smaller and so easier to analyze and work with. So we have this ratio, and by the same token we have 5 quarters here. So this is 5th harmonic, this is 4th. And, we have something that sounds nice, kind of, well, we know this is a major chord, but it occurs in these harmonics. It sounds quite nice. So we want to see if we can turn that, make a sort of harmonic system based around that, right? And so we have these frequencies. Like, let's say we just use the first 5 harmonics, but we can also construct further frequencies from these. So, for example, if I take this 3/2 frequency, then we also already have 4/3 here. But this can also be just stacked on top of the octave, right? We can take this frequency and apply it down here. And so we've constructed our ratio of 4/3, which is a perfect fourth. So we have this note in our scale now. And likewise, we have, this is 5/4, this is 6/5. But apply this to C, and you end up with 6/5 over C, the minor thirds. Right? So we've kind of inverted these two notes in that sense. We've basically said what ratio do we need to multiply this ratio to get to this simpler ratio, like to get from the 5th to the octave is by a 4th, or to get from the major third to the perfect 5th is by a minor third. And we can actually just keep doing that process in a few different ways. We can invert over the octave the major third, for example. So, this is 5/4, this is 8/5, and so you so this is from, what is it, sorry, 1, 2, 3, 4, fourth harmonic. So this is 5/4, 6th, 7th, 8th. This is 8/5, which is if we apply it to our roots note, gives us a minor 6th. That's the same ratio. And likewise, we can construct a major 6th by inverting the minor thirds that we already had. So our minor third was this one, 6/5, right? And we can go from there, apply this down here and get up to here, and then you end up doing 2 divided by 6/5, which gives you, what is it? 5/3, I think. Is that right? 5/3. Oh, that's interesting. Oh, it's just this ratio. Yeah, makes sense. 5th harmonic divided by 3rd harmonic, which is a major 6th. Which is this. Yeah. Stack 2 major 5ths on top of each other, you end up with this 9th. But of course, divide out the octave, you end up with a major 2nd. Invert that, you end up with a minor 7th. And likewise, you can add a 5th to a 3rd to get a major 7th. Invert that to get a minor 2nd, or just a semitone. Nice. And that's it, we've done that, and we've literally reconstructed every note except the tritone. The tritone is not too important, but it doesn't really matter too much for this analysis. The point is we have all these notes that are kind of almost equally spaced from each other, right? Which is interesting. So it's important to realize, right, that when we construct ratios like this, I'm showing you these ratios on this piano here, which is kind of like begging the question, because we already have 12 keys, and so it's like I'm trying to, I'm assuming that we already have the thing that we're trying to construct. So that's just because I'm trying to demonstrate it. Like, all of these ratios can basically just be constructed, using like just this string or whatever. But the problem is that if you do these constructions, you like the notes don't exactly match each other, right? So I said we've constructed these notes that are kind of quite equally spaced from each other. And if we can, we can construct these ratios in different ways. Like, for example, what happens, we said, like, if we have a fifth and we have 2/5, then we end up with that major second. But what happens if we put up another fifth? We end up with this ratio, which is a major sixth. But this isn't the same as the major sixth we already constructed, which is just the fifth harmonic divided by the third one, which is this. Right, on this piano it is the same. But if we actually just did this construction, we would get two ratios that are slightly different, right? So this one, where is it? This major sixth is 5/3, which is about 1.67. But this one that we constructed with stacking 3/5, right? That one is 27/16, which is 1.69. So not 1.67, but 1.69. So they're close. But, how close are they? I mean, if we constructed these like 12 notes, then all of our ratios are about, we've basically split 2 up into 12ths approximately. And so this difference of between 1.67 and 1.69, that's like a lot smaller than a 12th in terms of ratio. I mean, I'm fudging the maths a little bit, explaining it because it's logarithmic. But yeah, like they are pretty close to each other. And I think the best way to see it, right? I'm looking at my notes and yeah, I mean, if you want to be exact about this, right? What you can do in order to analyze this note is you can take, because our scale is split up into, it doubles every octave, and we're trying to split the octaves up into like pieces, that we can use to make songs. What you can do is you can look at these ratios and you can take the logarithm, right, of them base 2, right? And so if we assume that this is equal to 1, because why not, everything can be rescaled, then the logarithm base 2 of this is 0, and the logarithm of this is 1, 2, 3, 4, right? And so we want to kind of look at the numbers between 0 and 1, or 1 and 2, and multiply that by 12, and you get sort of how close these things are to like a 12-step equally spaced scale. And if you did that, then you would end up with, the stacking 3/5 major sixth. That would be, which one is that? Yeah, it would be 9.06, and the other one, which is from the third to the fifth harmonic, that would be 8.84. So like these numbers are very close to being whole numbers. Like 9.06 is close to 9, 8.84 is close to 9. And the best way to see this is if you just keep going and you keep stacking fifths. Like when you get to 12 fifths, those are the like sort of 12 equally spaced notes in the octave, you end up with a ratio of 1.5 to the power of 12, which is, you take logarithm base 2 of that, you get 7.02. And 2 to the 7 octaves, is of course 7. So 7 vs 7.02, they're very close to each other, right? They're about, a quarter of a semitone off, yeah, because like a semitone would be a 12th, which is about 0.08. And this is 0.02-ish. So that's kind of where the idea of equal temperament scales comes from, where we're going to define all of these notes to be equally spaced within the octave. So the ratio between these two notes is by definition the 12th root of 2, so that whenever we multiply them up together, we just end up with, that squared, that cubed, up until that's the power of 12, which is the octave, and so if you take the logarithm, you'll end up with equal spaces of a 12th. And yeah, that's basically how that was invented. So, historically speaking, there are still lots of instruments that are tuned using exact ratios, like the 3/5 and all that nice stuff. Whoops, this is 3/5. And you know, you can still do that. And if you do that, then if you play in a different key, the keys are going to sound different to each other because the ratios are going to be slightly off. And so, like for classical musicians, this was like, you know, no, these keys sound different, you know, and so people would compose for different keys, and it would say how you would tune the piano and all this stuff. But like for modern music, it was simplified so that things are just done in 12 tone equal temperament, which is the thing we've just managed to construct here. And hopefully, I managed to sort of clarify how that construction is done. I think this idea is natural enough that a lot of people sort of came to it independently. I think the first person who mathematically formalized this concept of 12 tone scales is a Chinese guy, and I wrote down his name using phonetic spelling, so I'll try to pronounce it. Zhu Zaiyu. Wait, no, I'll try that again. Zhu Zaiyu. That's better. Zhu Zaiyu. I can't speak Chinese, like the tones, but I tried. And yeah, that's basically that. So that is how we construct our scale. That is the next picture anyway, and it basically shows the exact concept that we're talking about. The 12 tone scale that has 12 equally spaced notes where we identified the octaves, and that's how the notes are named, right? So like C is the note at the top there, and then as you go around the circle, you get the 12 notes, and those keep repeating as you go up in pitch, right? So that's that. So to bring it back, right, to what we were talking about, we constructed all these notes pretty much by first constructing the octaves and then putting all the notes in between. And we constructed this circle of semitones in that way by identifying every note that is separated by an octave. So this is C, this is D, this is E, you know, this is E flat. Like all these notes are kind of considered equivalent to each other. So that explains the octave, the second harmonic, but then the next simplest ratio is the third harmonic. And don't forget, we basically constructed out an entire scale, or like we showed we can construct the entire scale by basically just iterating this fifth, you know, this ratio, because once you iterate it 12 times, you get something that's very close to an octave. And in fact, you do actually get every note in between as well, because, well, basically because this fifth within this system ends up being 7 semitones, and 7 is co-prime to 12 in maths. Don't worry about what that means if you don't know, but it basically, geometrically, we can show you what it means. You basically get this pattern. So, you know, you start from C, and you go up by this ratio, this perfect fifth. Don't forget, the perfect fifth, the simplest ratio we have that isn't an octave, 3 halves. Or just, if you ignore the octave, 3, just a ratio of 3. But yeah, basically that ratio is like the building block, right? And so we go from C up to G. So if you follow the line from C to the left to G, and then you just keep following that line, and you end up with C, G, D, A, E, B, F sharp, C sharp, yeah, and then A flat. I mean, whether I've written them as flat or sharp is not important for now. You should consider them the same thing. I'll explain later on the nuance there. But yeah, basically that. And so because that does literally trace out every note in our 12 notes, this star-shaped, I think that's I'm just putting random blur references in all of my tutorial videos. Because it does that, we can actually basically just make that the circle instead of the... Did I call it a fucking pentagram? It's a dodecagram, sorry, because it's like a star, that a 12-pointed star if you look on the inside. Pentagram is like the whole satanic thing. A 5-pointed star is a pentagram. Right, so we can basically invert the thing, right? So we can do this. And so now it's arranged in the order of the fifths, C, G, D, A, E, B, F sharp, whatever. And if you follow the dodecagram shape, the star shapes, you end up going C, C sharp, D, E flat, E, F, F sharp. So it's the same thing we had before. We basically just swapped the order of the things around, right? And lo and behold, we have just made the circle of fifths. So that's it. The reason the circle of fifths is so fundamental to how harmony works and just everything in terms of sound is because it is basically the fifth, which is like the single step along the circle of fifths. This interval is the simplest interval in the harmonics other than the octave, and the octave is basically too simple in the sense that octaves actually do sound literally the same to us. So this is basically the simplest, not the same sounding thing, which is like the simplest form of color, the most fundamental form of color, right? And so that's why it is so fundamental. We can actually basically construct our scales from the circle of fifths. That's how like fundamental it is. So like we can basically think of it that way. Basically, the notes that are close to each other on the circle of fifths are the notes that sound the most similar to each other. So the most similar sounding notes to C are F and G. And the most similar sounding notes to F are B flat and C. And to G it's C and D, right? And etc. So we can basically consider now how we can make a scale out of these notes. So let's say we want like a kind of happy sounding scale, like a majorish scale. And by that we basically mean second harmonic, third, fourth, fifth, sixth, like something that captures this sound. And basically we can construct this major thirds out of fifths by just stacking fifths up, because we can get to literally any note by stacking fifths up. And so we can just do that, right? So we start with C and then G. So we're going around clockwise around the circle of fifths. We have D, A, and then E. And so suddenly we have the major thirds that we want, and we have the major third chord as well, which is this. And so here we have a 5-note scale. We can basically put this together, so it's C, G, D, A, E, which is C, G, D, A, E. And that's it. And the scale has a name. It's the major pentatonic scale. It's pentatonic in the sense of, which means it has 5 notes in it, basically. But we can literally just play music in this scale, and it's the kind of pentatonic sort of Eastern sounding scale, like stereotypically associated with Chinese music, which is often pentatonic, I think. I know very little about non-Western music, so I shouldn't really say anything about it. But yeah, pretty much. So if we wanted to add a bit more depth, right, to our scale, which now has these 5 notes in it, which is just stacking fifths along the circle of fifths. Well, all of the intervals between our notes are either tones, like 2 semitones, or they are 3 semitones. So we can probably fit in more notes in. We can keep putting fifths in. So, C, G, D, A, E, B, F sharp, right? And that gives us 7 notes. And then we can put in C sharp as well. And that gives us 8 notes. But why is C sharp going a bit too far? Because now we have all of these 3 notes in our scale, so it's kind of becoming a little bit bloated, right? So maybe we stop after 7, which gives us where is it? Sorry, dum, dum, boom, boom, boom. I'm not actually singing them, but yeah, basically these notes, which is the same as saying keep fucking it up because of my thumb. And you'll find, if your memory is any good, that we have basically just constructed the Lydian scale. And that's how we did it, right? So this scale has a couple of semitones in it, gaps of one semitone, but they're all basically splits among tones, so you don't have two semitones in a row, and you don't have like any gaps of three semitones. So these are kind of the most regular scales that kind of fill up the 12-tone scale, and they have size 7. But we needn't really stop there, because, you know, there's no reason that our C-based scale, so in the key of C, there's no reason that that should comprise solely notes that are on the right on the circle of fifths. So, I mean, the notes on the right of the circle of fifths are inherently more stable, and the reason for that is because they agree with the harmonic series, which has a fifth in it. You know, harmonic series doesn't have a fourth in it. That requires you to basically construct it, but this is kind of naturally more consonant. It's already there, right? So, but nonetheless, we can, if we want to, just get rid of the notes all the way to the right and instead include some of the notes on the left, so go anti-clockwise, right? So let's say we take our Lydian scale, which is all of the notes on the right half of the circle of fifths, from C to F sharp inclusive. We delete the one on the end, which is F sharp, and we put the one on the left of C, which is F. And so now we have, that's in the order of fifths, and that's in the order of semitones. So that's it, we now have the major scale. We can do this exact same process another few times. We get rid of the notes all the way on the right, so the B, and we include the next note on the left, which is B flat. So B gets flattened to B flat. E gets flattened to E flat if we go again, and A gets flattened to A flat if we go again, and suddenly we've, after 3 steps, or like 3 steps relative to the major scale, we have the natural minor scale. So this is a little diagrammic representation. So those 5 scales that we were talking about, which we had already basically sorted in order of happiness, we now have them here, sorted along the circle of fifths in the exact order that we would expect them to be in. And so this is really starting to shed some light on why these scales sound happy and sad, and we're starting to get to the generalization of happiness and sadness. That is brightness, the thing that we've been trying to construct, right? So there are several consequences of this, right? Of this model that we've come up with and this diagram that I'm showing. So like, we've defined brightness, you know, I mean, I haven't specifically said it, but like you can see that everything is basically laid out in terms of an order of notes and an order of scales. So we know what brightness is. So like, for example, the Dorian scale has brightness -2 relative to the major scale, right? And not only do the scales have brightness, but like, and the brightness of a scale is like how far along the circle of fifths it is, right? So if you shift the scale by 1 to the left, the brightness goes down by 1. If you shift it 1 to the right, it goes up by 1. So like -3 for minor up to +1 for Lydian, right? Natural minor. But yeah, not only do the scales have brightness, but the actual notes within the scale are also ordered in the same way, and so all of the notes have their own brightness within the scale, or even like outside the scale, just relative to the key. Those notes have brightnesses. And so, you know, the key has brightness 0, let's say, and then, you know, you can look at the circle of fifths and you can go, well, okay, in the key of C, G has brightness +1, D is +2. It's literally just how far around the scale it is, right? So that's another consequence. And more than that, then, within each scale, there is clearly a brightest note and a darkest note. And we literally change the scales by like removing the brightest note and replacing it with the next darkest note. You know, that's what we've been doing. That's how we got from Lydian to major to Mixolydian to Dorian to minor. So not only that, but like we have a generalized scale now. We don't have to like stick to 7 notes. We can play in however many notes we want. So you remember when I was doing the Mixolydian demonstration and I said like, okay, well, Mixolydian is, what was it? So like Mixolydian is like, and you know, we were like jamming in Mixolydian and it was all like, and you can just throw this note in as well, like I was saying, the blue note, you know, well, this is an accidental, it's a Mixolydian, but it's just literally the note 1 to the left of Mixolydian, so it's like the next note along in the dark side, right? So we could just think of this as being 8 notes, an 8-note scale that includes both the minor thirds. Do you remember this? So like the Hendrix chord. So it includes both the minor third and the major third, right? And then this is sort of on the dark side and this is on the bright side, right? So like, yeah, I mean, we're just playing in a generalized scale. We don't really care exactly what the scale is. We're not, you know, we know like for all of the accidentals that are not in the scale, we know like how far away they are. So obviously like in Mixolydian, this note is still pretty consonant for Mixolydian, and it's more consonant than the next note in the scale, which would be, I'll actually use my own diagram here. So instead of E flat, it would be A flat. So like this note, you know, this is more dissonant than this. Like this is more dissonant than this, and this tells us that. So we know if we want to play outside the scale, we know which notes still sound tame and which notes sound like shocking. So, you know, we have that as well. And we're not constrained. Yeah, so we're not constrained to play in the scale. You know, you can literally shift around, you can kind of change the scale around, and like every key change can just be interpreted as shifting around the circle of fifths to a new scale, relative to the same key, you know. So everything can just be relative to the original key, and that clarifies the size of a key change, for example, is like how many notes change when you shift the scale around, you know. So we could have like, if we shift from, well, I'll do an example of this later, but for example, we have like this kind of D Mixolydian-ish thing, and you know, we can shift into like F major. Then just by looking at which notes we have, we realize that is a key change of -2 brightness, and it sounds, you know, you can tell eventually it basically sounds like it. So this brightens up to this, and of course the F brightens up to this, and that's the change. And so this is 2 steps brighter than this, right? Dark, bright, and you can tell the difference is 2. So yeah, not only are we not constrained to play in the scale, but even the root doesn't actually have to be in the scale. We can define like a 7-note scale that doesn't include its own root. You know, we could like take the Lydian scale and extend it by 1. So this is Lydian, and then the next note along is this one. So relative to C, the scale then sounds like, so it sounds pretty eerie, very bright. Right, so that's like the meta-Lydian scale, like the next scale along. So like, you know, it's a very liberating way of thinking about things, and it has all of these interesting consequences. And I'm gonna give an example of in what ways these scales that don't even contain their own roots can be useful. You definitely can make sense of them. It's all about the context. But yeah, I think for me this is very much a nice way of thinking about things that just kind of simplifies a lot of the confusion around key changes in there. It means you can make sense of things and have like retain a fixed reference point. You know, you stick to your key, and then you can make sense of the whole song relative to your like original key. You don't have to think of it as the key really changing, if that makes sense. So it's all a point of view, a frame of reference. All right. This is the most difficult part of the video to record for sure, because explaining this concisely is not easy. It's definitely the theoretically hardest part of the video. But it is just for fun, really, or like for interest, for a bit of maths. It's not really that practically applicable. So you can definitely skip this section and move straight on to the worked examples, the next chapter, if you want. But, you know, let's just do it for fun. So here we go. Right. Think of the semitones. So the semitones, we've already modeled them as a circle, right? A circle that looks like this, but they are also a line. It is literally just all of the notes going up the whole piano. And so we have two different ways of thinking about them, right? We have the line, and then we also have the circle. So the circle is kind of like we identify all the octaves, and then it kind of loops. But, you know, the circle discards some information because it says that like this C is the same as this C because they kind of sound the same. But those notes are still different. And so one way we can think of them as both a line and a circle at the same time is as a helix, which is this slinky shape that I have, right? So what is this shape, right? It's basically like a circle. It's like you're drawing a circle, but while you're drawing the circle, you're kind of slowly moving your arm down, and so it kind of spirals over itself, right? That's what a helix is. And so the line, because it is just like one bit of wire that this is made from, the line is all of the semitones, right? But if we look at it from this angle, then we see the circle. So basically what we're saying is, you know, when we look at it along the circle, we go like, I'm not going to name all the notes, but it's kind of like C, D, E, F, G, A, B, C. We make a full circle, right? But what's actually happening is like, say C, like say we're at C here actually, and then we go C, D, E, F, G, A, B, C. And so we're at a different C that's vertically directly above this C. But we're still just going up the notes C, D, E, F, G, A, B, C, you know, so it's like we're consistently going up the piano as we go up the helix. But every time we kind of get to the same place on the circle, so like directly above, that's an octave, right? So C to C is like here, and then this is D and D, E and D. You get me? So that's basically how the helix of semitones works. And you have two different ways of thinking about it. You can think of it as going along the helix, or you can think of vertical lines that identify all of the octaves, right? So my question to you basically is, you know, we have this helix of semitones, where first we had the circle of semitones, and now we have the helix of semitones. So my question is, if we look at the circle of fifths, can we think of a helix of fifths? Does that concept make sense? So you can pause the video if you want to think about that for a bit. And here's my answer for you. So pitch loops, right? So as we go up the piano, it loops around on itself, but the pitch itself keeps getting higher. The actual character of the notes keeps kind of coming back to what it was before. So C has become C again, and we don't really hear much of a difference between these two. So my question is, does brightness loop the same way? So like if we come back from C to C, or like say we've gone all the way around the circle of fifths, does that note sound the same as the original note, in the same way that C an octave above sounds the same as the C below? At least in terms of harmony, they sound very similar. And it doesn't, does it? Because like brightness doesn't loop, because if you go around the right side of the circle of fifths, right, like this, then the notes keep getting brighter, and if you go around the dark side, they keep getting darker. So like, say we get to F sharp, the note on the opposite end of our reference C, right? So is that brighter or darker then? Does it loop back? Like, can we go like brighter and then suddenly we're at the dark notes? But like literally every note, the further away we get in either direction is even further away. It's like the notes get darker and darker and darker on the left, or brighter and brighter and brighter on the right, right? And so F sharp, for example, like we already know what that is because it's in the Lydian scale, right? Which covers the bright half of the circle of fifths, or like starting from C. So it has this note in it, which is a very bright sounding note, right? So like you can hear that brightness there, and so you wouldn't expect the same brightness to be audible on the dark side, would you? That's the question. And so let's try to do that, right? We don't have the dark version of F sharp in any of our scales, like in this diagram, but we can still kind of construct it, right? And so I'll take you through a way of doing that. Like the darkest scale that we have that is kind of stable and we can just kind of jam in is the minor scale, right? And what we can do is we can basically go even darker. So like the construction that we did to get from Lydian to minor, where we would always take off the brightest note and replace it with the darker one, and then cycle through all the scales by doing that. So like that's how we got from Lydian to major to Mixolydian to Dorian to minor. But you know, if people who are familiar with the modes know that there are another two modes there that I haven't mentioned, and you can construct them the exact same way. You can go further. From minor, you just delete the brightest note. This bright note here, you delete it and replace it with the next darkest note. So this is called the Phrygian scale. And then we do that again. The brightest one that's left is this. We replace it with this and we end up with the Locrian. But we can't really, I mean, these scales are really rare in isolation and they're hard to jam in because like they're unstable, they sound dissonant, right? And so you can't kind of just jam in them by yourself. And that's the reason I didn't include them. Like there are other scales, right? That are more stable than these, that are not related to the five that I've mentioned. There's stuff like harmonic minor and Phrygian dominant, you know, scales that are used in like heavy metal or Arabic music. I would even say like the fucking whole tone scale is more stable, you know, it's fucking scale made up of just tones that goes like some fucking film of music and that kind of a thing. But nonetheless, we definitely can make sense of these dark, unstable scales, right? And so the way to make sense of them is to just kind of add in a bit more context, right? So we can kind of jam our way through, start with the stable natural minor scale, and then just get darker by replacing the brightest note with the darkest note, you know, and we can just do that for a bit. So let me show that off. So this is our minor scale. And it sounds like its characteristic chords, of course. So we can kind of just play like this. So there we go, like I've just darkened this, what used to be the brightest note D, into D flat. very dark note there, so we've replaced G with G flat. That's the epically dark. This note, which is I've replaced C with C flat. And so you see what I've done there, right? So I've basically just deleted the brightest note and replaced it with the darker one and shifted the scale around the circle of fifths to the left 3 times. And you can see by looking at the circle of fifths diagram which notes I've used, right? So I started with minor, with like the A flat as the darkest one, and then I kicked out the D and put in a D flat instead, which is the same as C sharp, and then G became G flat, which is the same as F sharp, and then C became C flat, which is the same as B flat. B. Yeah, it's the same as B, right? So you can actually shift it so far that you lose the original key. But yeah, we've constructed these increasingly dark notes, and that's kind of what I was getting at, right? So like, yeah. So just by playing, you know, like this, we can get to this dark note, which is the F sharp, which I just called the G flat. And that's the note we were trying to get to. But don't forget that's literally the same note as... which is so bright, isn't it? But this sounds like super dark, super eerie, super bright. That's basically it, right? So like, what's going on there? We have the same note, but it's not the same note. But it's literally the same note. So like, you know. So what's actually going on, right, is that these are not the same note. And they're not the same note because one of them is F sharp and the other one is G flat. That's one way of thinking about it. But this is probably the way, the helix is the way that I think most clearly explains what's going on. So if we're thinking of this in terms of the circle of fifths, then we're looking at the circle still, right? And so C is here, right? And then if we go around the bright side of the circle, we end up at F sharp, the bright note that we like. But if we go around the dark side, we end up at G flat, but they're the same note. And so the circle of fifths is kind of not very useful because it's telling us that these two notes, which sound really different, are actually the same note. But if we turn the circle into a helix, we end up with something completely different. So we're at C, let's say it's here, or like, yeah, here. And, you know, as we go up the line, up the helix of fifths, things get brighter. And as we go down, they get darker. And so from C, we go up to F sharp, which is here, or we can go down to G flat, which is here. The two notes are directly above each other because they are the same note. However, the fact that they're, you know, separate on the helix, and the fact that to get from one to the other you have to travel past 12 notes, an entire octave, like you have to do a whole loop, that demonstrates that these are actually different notes. And in fact, you know, we can think of it past just F sharp and G flat. So like we were at C, but like as we constructed these notes, if you remember, we constructed first of all, you know, D flat, the Phrygian note, and then we constructed G flat, and then we even managed to construct C flat, which is actually B. So we went, you know, from C downwards, past all of the minor notes, of which the darkest is, I think, A flat. Yeah. And then we went to, from A flat, we went down to D flat, and then to G flat, and then to C flat. But these notes are the same as, going in the opposite direction, C flat is the same as B, G flat is the same as F sharp, and D flat is the same as C sharp, right? And we haven't heard what C sharp sounds like yet, but C sharp's actually very easy to construct as well. So we just make F sharp even brighter, right? So You hear this like bright little fluffy note right at the top. You know, it sounds a little bit eerie. It's a little bit too bright almost compared to the F sharp, certainly. But that's it, it's literally that note. And that's the same note that we constructed earlier on as we were going darker as the Phrygian notes. The really creepy one. It's the same note. So we've actually managed to duplicate 3 notes, not just one, in the context of a bright copy of each note and a dark one. And that's just us going along the helix, you know, further in this direction and further in this direction. And that's basically that. You can actually keep going around the helix as much as you want, you know, it wraps around itself. Yeah, and if you're wondering why it's so much easier to construct bright notes than dark notes, it's because of the harmonic series, if you remember. Like, the harmonic series has baked into it the 5th and the major 3rd and these notes from the bright side, whereas in order to go darker, you kind of have to like invert that and end up with, you know, all of these darker notes. And so they're not like, they don't sound as good or as consonant because they're not like naturally baked into the harmonic series as much. And that's why it's so easy to just go like, you know, into brighter and brighter territory. So this is E sharp. At least I think it is, I'm not even sure. But yeah, that's kind of it then. So like, you know, the helix keeps wrapping around as you go up and as you go down, and it keeps similar sounding notes together, which is kind of the point. We have like the bright copies of, you know, these notes, and we have the dark copies of the same notes, but they're kind of kept together on different rungs of the helix. So like the dark ones are here and the bright ones are here, but they're all directly above each other to represent that they are actually the same notes out of context. And that's kind of the point. Context is key. The reason why the notes, you know, let's say we want this note to sound like something, the reason it sounds bright is because of the other notes we play with it. The bright side of the scale. So we're playing, this is the brightest note, and then we're playing other notes that are less bright, they're more stable, closer to the key. And the same thing happens if we want this to be dark. We just play it with dark notes. You know, like that. And so, yeah, pretty much context is what makes it sound like that. And you want to include basically more stable notes that are like, say we want to have our +6 brightness note, this one, then we're going to include some of the like +4s, +3s as well to give it context that makes it sound like a +6. We want to include notes that sound similar to that note, and that's kind of how we manage to distinguish them basically and get them to sound different. I have a fucking cold, so it's all tissues and crying everywhere. But yeah, basically, to take this concept to its natural mathematical conclusion, and this is really getting into the stuff that is like wank, because this isn't practically applicable for musicians at all. But like, you know, as is implied by the helix, you can keep going as far as you want. You can keep going around multiple loops of the helix and get into brighter and brighter and brighter notes, right? So you can construct infinitely many notes like this, and you can keep constructing them by basically going like, you see the pattern in the circle of fifths, right? So we have 2 different ways to construct notes. We can go note by note along the helix, or we can go along by redefining the same notes on different rungs of the barrier of the helix, right? So in order to go along the helix, you look at the circle of fifths, right? And it says like F, C, G, D, A, E, B. So the pattern, that pattern, we just keep repeating it, and then we just add like a sharp. So F, C, G, D, A, E, B, F sharp, C sharp, as you can see on the picture. And then it goes further, G sharp, D sharp, A sharp, E sharp, B sharp. So E sharp is F, B sharp is C. And then it keeps going, right? So F double sharp, C double sharp, G double sharp, D double sharp, A double sharp. as much as you want. Just keep going around the helix. And if you want to go the other way, you do the same thing in reverse, right? So B, E, A, D, G, C, F, B flat, E flat, A flat, as you can see in the picture. And then it keeps going D flat, G flat, C flat, F flat. So those are some of the notes we were talking about earlier. C flat being B, F flat being E, and then, you know, B double flat, E double flat, A double flat. And if you want to go up and down the helix in order to get, you know, to jump 12 notes, basically 12 steps in brightness, then you're getting back to the same notes, at least without further context, it's the same notes. And so in order to do that, let's say we have like F sharp and G flat we were talking about, so like C, F sharp, or if you go down, G flat. So we can go further down, we just increase the letter, right, to go further down, A, and then put in as many flats as we need to make it the same note. So F sharp is the same as G flat, is the same as A triple flat, is the same as B quintuple flat, which is C sextuple flat. And in the opposite direction it works as well. So F sharp is the same as E double sharp, which is the same as D quadruple sharp, which is the same as C sextuple sharp, and yeah, just like that you can make infinitely many notes. It's completely useless, right? Like, it's not practical for musicians. And why is it not practical? So this is an interesting question. Why is it not practical? Because like even F sharp and G flat, they cannot be played at the same time because they sound the same, right? They would sound in context like either F sharp or G flat, or without context, just kind of this neutral tritone sound. Because the context is just not there. So the stuff that is needed to make F sharp sound like F sharp, these notes make it not sound like G flat. So if you want it to sound like G flat, you need to not play these notes and instead like play the darker notes. And now that sounds like G flat, right? So we can hear G flat and F sharp at the same time because we can kind of play these chords side by side. So we can actually hear that note and the contrast between the -6 brightness G flat and the +6 brightness F sharp. So we can hear like this contrast of 12. But if we wanted to go up to like 30 or some number like that, you wouldn't be able to do that at all because the context that you need will have been completely lost. You know, you can't hold that many notes in your head to imagine what the harmony is sounding like. You can't make sense of it anymore. So I always think like I could compose a song that starts at like a particular key, like C, and then just keeps getting brighter, and then like we end up at the notes that are like 100 brightness or whatever. You know, you just keep going. Whoops. So now we're at this. Yeah, you know, you just keep going up until you get to like 100. But then, like, if I jump in the middle of that composition, then it just doesn't sound like C. The original C is the key anymore. Like, the key's kind of changed because you can't keep enough context there in order to kind of reference the fact that that sounds like the original key. You know, you can just about, if you keep stacking fifths starting from like a really deep down note, then you can just about manage to make it sound like some of these notes are like really bright compared to this. But like you know, you can't do that with it. You can't like stack 100 fifths at the same time. You need like some gigantic piano and it's fucking supersonic, and it would literally be supersonic, I think. So yeah, that's basically the reason, if that makes sense. And so what does that mean? It means that, you know, I'm going to go into some practical examples now. And it's all just going to be a lot tamer and calmer. Like, for practical purposes, we fix on local context. Like, if you look at a particular section of the circle of fifths, I'm still crying because I'm still ill, but I just don't have time to keep putting off recording this video. So we fixate on a little segment of the circle of fifths, which typically has like somewhere between 7 and 9 notes, which includes, you know, the possibility to do a few key changes. And that's pretty much what I'm going to do. Like in the future examples, it's just going to be like a few notes, a couple of scales, or like a couple of 7-note scales that fit into like a kind of generalized 9-note scale, and that's it. Like it's easy to keep that context in your head because it doesn't go far enough around the circle of fifths where it like wraps around and starts to get ambiguous, you know, where you have to like have a lot of context to tell what the note is supposed to sound like. So there you go. This is a bit of head in the clouds stuff, or head up your ass if that's how you prefer to think about it. But I hope you enjoyed it still, and we'll get back into the solid ground stuff and do some of the practical stuff that is actually useful for musicians in the next chapter.